Alright guys, welcome to video 4.2.2 where we'll do examples 3 and 4 together. Alright, consider a 0.1 molar, make sure you memorize this. This is acetic acid or vinegar solution. Find the concentration of all species, the pH and pOH, and the percent ionization. And then they're giving you the Ka for vinegar here. So, knowing that this is vinegar, you know this is a weak acid. Acetic acid is a weak acid. And so just like our KSP that we did before, we're going to be using an ice table. So ice table. And then you're going to need to use a Ka equation. So you're going to use an ice table and your Ka equation. So Ka equals blah, 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 blah. And then we'll see that when we get there. So remember, first step. First thing we're always going to do, write a chemical equation. So let's see what's happening here chemically. So we have HC2, H3, O2, double-sided arrow because that's a weak acid, dissociates into H plus your acetate anion, C2, H3, O2 minus, ICE. Okay, so here we're starting with 0.1 molar acetate, so acetic acid, 0.100. And of course we don't have any products yet. Now, unlike the strong acids and strong bases, we know that this is weak, so we know it doesn't dissociate 100%. We don't know how much is going to come off, so it's going to be, again, the plus X minus X thing that we were doing before, just like with your KSPs and your sparingly soluble salts. So in the end, we get 0.100 minus X, X, and X. Okay, that's the ice table part. Now let's do the Ka part. So my Ka equation equals products over reactants. Now there's no solids and no pure liquids here, no gases, no nothing else. They're all aqueous. They're all going to be included in Ka. So Ka is products over reactants, always. So always products over reactants. So H plus times the concentration of acetate over my reactants, because again this is an aqueous solution. You can tell it's a solution because molar. Of acetic acid. And then our Ka is given to us here, so 1.8 times 10 to the negative 5. Plugging in actual numbers for this, we get Ka is equal to X times X, so just X squared, over 1.0 times 10 to the negative, 0.1 minus X right here. So 0.100 minus X. Now just like before when we were doing KSP, we can assume that this X is much, much smaller than 0.1 molar. And in fact it's going to be, because this acetic acid dissociates to such a small amount because it's a weak acid. So we can safely go ahead and ignore that X there. And so this ends up getting you X squared over 0.100 equals 1.8 times 10 to the negative 5. Therefore, when you plug this in, your X is going to be equal to 1.3 times 10 to the negative 3. So that means 1.3 times 10 to the negative 3 is the amount of hydrogen ions that came off. And if you want to check your assumption here, you can type in 0.100 minus 1.3 times 10 to the negative 3, and you'll note that it's still 0.1 after you take into account sig figs, right? So it doesn't really matter, and it's totally, completely fine to ignore that X. Okay, let's move on to the second part of our problem and find the concentration of all of our species. So first, let's find the concentration of our acetic acid here. So HC2, H3, O2, memorize that, equals 0.100 minus X, I believe minus X, which is going to be 0.100 minus 1.3 times 10 to the negative third, and that's going to give you 0.099 molar. Okay, next species, H plus. And our H plus is just X, which was 1.3 times 10 to the negative 3. Concentration of acetate equals X, so again, still 1.3 times 10 to the negative 3, because that was just x. Okay, so I'm going to draw a little line here so we don't get confused, and then we're going to go ahead and move up here. So let's find the pH. pH equals negative log concentration of H plus. So the concentration of H plus is 1.3 times 10 to the negative 3. When you plug that into your calculator, you should get 2.87 as your pH. pOH, now you could go and you could find the hydrogen or the hydroxide ion concentration from H plus, and you can do pOH equals negative log of the concentration of hydroxide, or you can just do pOH equals 14 minus your pH, 2.87, and get your pOH that way. So there are many ways to solve these problems. Just choose whatever one is easiest for you. So subtracting here, get 11.13. Now from the pOH, it's really easy to go backwards and get your pH. Remember that your equation for the concentration of the hydroxide ions is 10 to the negative pOH. We just solve for a pOH, so it's 10 to the negative 11.13. And then when you plug that in, it ends up being 7.4 times 10 to the negative 12 molar. So we really have a very small concentration there of hydroxide ions in solution. They're still there. Your percent dissociation equals x over whatever your initial is. I don't think I gave you that exact formula last time, but I was just telling you what to put where, but now you have your generic formula. So your x, whatever your x is going to be on top, and your I is your initial amount of whatever is not broken up yet, either your acid or your base. So your x in this case was 1.3 times 10 to the negative 3 over your initial amount, so that's going to be 0.100 molar. Plug that in, multiply by 100, and you get 1.3%. So when we say this is a weak acid, we really mean it's a weak acid, right? So if you put 100 molecules in here, only 1.3% of them, or only 1.3 of them on average, will break up, and the rest are just going to stay your acetic acid, and they're not going to break up at all. Okay, that is the end of that problem. Let's go to example number 4. Example number 4 is talking to us about ammonia. Now, ammonia is another good one to memorize. So this is ammonia, and you should memorize that, because that is a classic example of a base. Ammonia, memorize it. Classic example of a weak base. So we have a 0.1 molar weak base ammonia solution. So this type is a weak base. The strategy is going to be the same as before. We're finding all the same things. They're giving us the Kb this time. Notice they're giving us the Kb and not the Ka, B for base, and of course A is for acid when you have an acid. So your strategy is going to be the same. You're going to use an ice table and Kb. Okay, I would like you to pause this video, and just like last time, please tackle this problem on your own until the very end. I don't believe there's anything really tricky about it, except for realizing you need to use Kb and not Ka. So go ahead and solve that and come back. Taking a look now at example 4. Remember, the first thing you're going to have to do is write an equation for dissociation. So NH3, now we can write this plus water. So you don't have to write it plus water, but I'm going to show you why. Plus H2O, double-sided arrow. Now remember, the ammonia actually pulls that hydrogen ion from the water, because the water is acting as the acid in this case. And so you end up getting NH4 plus OH minus. Now that water is a liquid, so it's not going to count at all. So it would be totally fine if you just wrote just that. NH3 goes to NH4 plus OH minus. I just wanted to show you where that came from. So ICE, initial change end. So we're starting with 0.100 molar here. We don't have any dissociation yet. Of course, this is weak, so we don't know how much it's going to be. So minus x plus x plus x, 0.100 minus x, x and x. Okay. So let's do our Kb expression. And let's go ahead and figure out what X is. So Kb is going to be equal to products over reactants. H2O, of course, is a pure liquid, so that is not going to be included in your Kb expression. So our products, the concentration of NH4 plus times the concentration of hydroxide. And if you were to have a coefficient here, for example, a 2, that would be squared, just like before. But right now we don't, so it's an invisible 1. Over my reactant, so NH3. And our Kb here is given to us, 1.8 times 10 to the negative 5. Okay, so Kb then equals x times x, which is x squared, over 1.0 minus x. I'm going to go ahead and ignore that x, assume it's very small in comparison to 0.1. So I end up getting this. So that's equal to 1.8 times 10 to the negative 5, just bringing down my Kb there. Solving in your calculator, of course, you multiply there, take the square root of what you get, and you should get x is equal to 1.3 times 10 to the negative 3. Finding the concentration now of all of my species. Concentration of NH3 equals 0.100 minus x. So 0.100 minus x is 1.3 times 10 to the negative 3 equals 0.099 molar. Concentration of ammonium, NH4 plus here, is just x, which is 1.3 times 10 to the negative 3. Concentration of hydroxide, just x, 1.3 times 10 to the negative 3. Okay, let's move on the other side to find the rest. So I'm going to find POH first instead of pH first. Again, it doesn't matter what order you go in, just whatever's easier for you. But I already have my hydroxide ion concentration here. So I'm just going to find my POH first. POH equals negative log of the concentration of hydroxide ions, which equals negative log 1.3 times 10 to the negative 3, which when you plug that in should give you 2.87. 2.87. So that's my POH. And that's a good thing because my POH is very low, which indicates a base. Now I'm going to go ahead and find my pH. pH equals negative log of, or actually, sorry, I don't want to do it this way because I don't have my hydrogen ion concentration. I'm just going to go ahead and do 14 minus my POH, which is 2.87. And that gives me 11.13. So my pH, again, is high, which indicates a base, so that's another check that I can do as I'm going along in these problems to make sure I'm doing them correctly. So from my pH now, I can easily calculate my hydrogen ion concentration, because that equals 10 to the negative pH, which is 10 to the negative 11.13, which is 7.4 times 10 to the negative 12 molar. So not very many hydrogen ions in my solution here. Percent dissociation equals x over I. My x is 1.3 times 10 to the negative 3 over my initial amount of my ammonia, 0.100 times 100, and that's going to give me 1.3%. 1.3% of my ammonia is dissociated in solution.